Baik. Professor, for the access activity to the MATLAB problem, do we submit a code to
Yes, code 2.
code as well?
Yes.
As a zip form or what?
You can just do separate files.
Yeah.
All right, it's 5:30. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today? Good. Good. All right, so I graded your exams yesterday. Finished grading kind of late at night, but I got it done. So the average on the exam was 37 out of 50. So I have the exams with me today. So if you're here today, you can pick it up after class. So this would be a good time to just kind of remind everyone of kind of the policy we have in the class. Remember, we have two midterm exams. We have the first exam, which you just took on the direct stiffness stuff. And then we have the second exam that's scheduled for, I want to say week 13, week 14. There are two grade entries in on the for the midterm. So one of your midterms is going to be worth 30% of your grade. The other midterm is going to be worth 20% of your grade. So whichever midterm that you score higher on, I'm going to count that for 30% of your grade. And then whichever midterm you score lower on, I'm going to count that 20%. So if you didn't get the score that you wanted on this exam, just know that you can basically make up the points on the next exam. That one's worth 50% more. Okay. And if you did good on this exam, if you were happy with your score, then that's basically 30% of the points for this course kind of in the bag for you. So you can kind of take it a little bit easier for the second, right? So remember, I have this policy, I apply to all my courses now just to kind of, I know for exams, sometimes, things happen during exams, and so I want to give you guys an opportunity to have some flexibility, kind of bring your grade up. Okay. So definitely, definitely make use of that. Okay. The other announcement that I wanted to make today is ANSYS Activity 2. So that's all the ANSYS stuff along with all the code that's required at the end. So that's the last two problems. Originally, that was going to be due next Friday, March 29th. But then I forgot that next Friday is the comprehensive exam, which I know some of you are taking as well. So I've decided to push back the due date for ANSYS Activity 2. And so now it's going to be due on Tuesday, April 2nd at 11:59 p.m. Of course, that is over spring break. But I did want to give you guys a few extra days, just because I know probably a lot of you are cramming pretty hard for the comprehensive exam. Okay. Okay. I don't think I've changed it on Canvas just yet. I've kind of been running around a lot today, but I will do that as soon as I get back to the office after this. Okay. All right. And so with that, today we're starting a whole new thing. So we are, saying goodbye to the direct stiffness method. And we're starting kind of more what I consider to be more kind of general finite elements. And so if you took, this is kind of a more traditional finite elements treatment, where if you took finite elements at, from a lot of other kind of universities, this is kind of what you would learn. So you learn just straight from the equations, how to discretize the equations, how to kind of solve for the finite element solutions. So what we're going to learn from here on out is a lot closer to kind of what's implemented in softwares like ANSYS. Okay. Granted, we're going to be doing a simplified version of it, and so we're not going to be going full 3D. We are going to go up to 2D, but not 3D. But it's based on the same methodology. Okay. All right. Any questions I can answer before we get started for today? Okay. All right. So let's go ahead and get started. So the next couple lectures, we're actually going to step away from finite elements a little bit, just because it's all kind of important setup. And also I think it's good to kind of important to review differential equations as well for some of you that where it's kind of been a while. And so the title for this section is called Strong and Weak Forms. Okay. Strong and weak forms of boundary value problems. Okay. So probably a lot of terms that, you may have heard before, but, maybe not all together like this. Okay. So at the heart, or at the basis of every single finite element problem, every single finite element simulation is something called a boundary value problem. And that includes our direct stiffness stuff too. It's just that for the direct stiffness stuff, we took a few shortcuts to kind of, get to things like the truss equation, the frame equation, things like that. Okay. So a boundary value problem is essentially has kind of three main components. Okay. On the one hand, we have the geometry of the problem. Okay. So in kind of a more traditional sense, if in ANSYS, your geometry would be basically your CAD model, your digital representation of your geometry or the part that you want to simulate. Okay. The second component is the governing equations. Okay. So whatever part that you're interested in simulating, you want to basically simulate its behavior. And so its behavior is often governed by some equations. And more often than not, those equations are differential equations, oftentimes partial differential. Okay. And three is the boundary conditions. Okay. We've already talked about boundary conditions quite a bit in this class. Boundary conditions are just all of the external effects that are applied onto your structure, onto your geometry, to cause some behavior. Okay. And so boundary value problem consists of all three of these things. And the one part that we've kind of really been neglecting, that we haven't really paid a lot of attention to, is component number 2. Okay, the governing equations. So the governing equations for a lot of physical phenomenon, especially physical phenomenon that mechanical engineers deal with in their professional practice, are differential equations. And the thing with differential equations is that they are very difficult to solve, especially on an arbitrary geometry. Okay. So that was kind of the main motivation of how finite elements kind of came to be, right? And so in kind of the 17th, 18th century, scientists were really starting to discover that a lot of the physical phenomena or a lot of the way that the world behaves, can be governed by these differential equations, right? So they kind of use first principles. They use, conservation of mass, conservation of momentum, conservation of energy, things like that. And they developed this like really, sophisticated equations. The problem is that they developed all these equations, but they didn't really have a means to solve them on kind of arbitrary or complex geometries. So finite elements kind of has its roots in kind of applied mathematics. Finite elements was developed as a way to solve these differential equations. Okay? And through history, it's taken a lot of different forms, and so now, now finite elements is very, I would say, approachable in the sense that it's widely used or widely applied in a lot of commercial software that a lot of people kind of use, not in their everyday life, but in their professional life if they're an engineer. Okay. So what we're going to be focusing on over the next few weeks is exactly this process of kind of starting from a differential equation and how do we obtain a finite element problem from that differential equation. Because that's really the piece that we've kind of been missing. Because through the direct stiffness method, we got a lot of practice in solving a finite element problem, right? Element stiffness matrix, assembly, boundary conditions, solution. Okay. What we haven't really touched on at all is how do we even obtain those expressions for the element stiffness matrices to begin with, right? So all those element stiffness matrices that we've been working with for like the truss elements, the beam elements, the frame elements, the springs, they have their roots in an underlying differential equation. Okay. And the reason we're doing this now is to kind of show you that finite elements, it really is a very kind of flexible framework. So not only can you solve structural problems with this, but you can also use it to solve thermal equations, right? So heat transfer is also governed by a differential equation, the heat equation. You can use it to solve for fluid flow situations. For fluids, we have Navier-Stokes, okay? You can even solve electromagnetism, right? So finite elements, extends far beyond kind of structural mechanics that we've kind of seen in this class so far. As long as you have a differential equation, you can use finite elements to solve for its solution. Okay. And so to do this, we need to introduce a couple new concepts. Okay. Right. So differential equations can often be put into several different forms to make it either convenient or less convenient to solve. And we're going to present two forms today. So the first form is called the strong form. Okay. So the strong form is probably what you're most familiar with, probably the form of differential equations that you've seen in most of your previous math courses. Or if you're taking 438, 538, that's more than likely what you've been presented with is the strong form. But what we'll see is that we can take the strong form and derive something called the weak form. The weak form of a boundary value problem, the weak form of a differential equation that makes it actually, that kind of facilitates our finite element solution, okay? So the weak form probably most likely you've never seen before, probably because it doesn't really have a lot of applications outside of finite elements. But today, the plan for today is we're going to review the strong form. We're going to go over just some solution to some second order linear differential equations, and then we'll introduce the concept of the weak form and what that looks like. Okay. All right, but that's kind of the motivation and kind of the purpose of kind of where we're going to go for the rest of the class. Okay. Any questions on this so far? Okay. All right. So let's review some strong form. And to kind of illustrate this, I'm going to work on a very specific problem, which is 1D elasticity. Okay. So like I mentioned, the strong form is the more kind of traditional form, or kind of the more classical form for a differential equation. Right? And the reason for that is because if you were to take, kind of your standard conservation law, so conservation of mass, conservation of momentum, conservation of energy, right? When you apply those to kind of physical situations, it just very naturally kind of produces equations in this form. Okay? Okay. So I want to show you an example of this at using 1D elasticity as kind of the setting. Okay. Okay, so the 1D elasticity problem. So let's say that we have a truss element like this. Okay. Let's fix it to the wall on the right side. And then let's apply a compressive stress on the left. Okay. So the stress being applied on this side, just like that. Okay. So this T here, this is an applied compressive stress. Okay. So what we want to solve for in this case, or what we're interested in, is the distribution of displacement within this member. Okay. Because intuitively, what we expect is that if you take a structural member like this, you apply a force to it, right? Then the entire structure, because of elasticity, is going to deform, right? We expect the structure to kind of squish close to the wall, right? Very similar to what we had for ANSYS activity 2, okay? That we're applying the force parallel to the structure instead of perpendicular. Okay? So this function, or what we're solving for essentially is a function u of x, right? Where u of x is going to tell us how much deflection or how much displacement we're going to experience in the rod as a function of distance x. Okay, so if we draw kind of the coordinate axis here, I wish I didn't use red for that, right? So we're going to say the positive x-axis is going to go from that direction. Okay, so we have our origin here, so our value of x is equal to 0 was on the left side of the rod. And then going from the left side of the rod towards the wall, that's going to be increasing value. Okay? And what we want to solve for here is a continuous kind of function, u of x, that tells us what the displacement is as a function of x. Okay. All right. So let's say that this rod here has a length L. And additionally, one thing that we haven't considered before is let's assume that there's some kind of body force inside the rod. Okay. Let's use. So in green right here, I have B of x, which is some body force. Okay? So if you've never heard the term body force, a body force is a force that's kind of felt throughout the entire kind of volume or on the interior of the structure. Okay. There's a very classical body force that everyone experiences every day of their life at every moment, which is gravity, right? So when you experience a gravity force, the force that kind of pulls you down towards the surface of the earth, that is what we call a body force. It's kind of like an internal force that kind of pulls you in a certain direction. Okay. It might seem strange to have a body force that kind of goes horizontally like this, but another very classical body force is like an electromagnetic force. And so maybe this rod is electrified, or it's made of some metal, and there's a magnetic force that's kind of pushing it inside or pulling it out. Okay. The exact origin of the body force isn't that important in this case. We just have to kind of account for its existence. Okay, so just because just so that we can account for it in our equations. Okay, so that's the situation that we're working with now. And so the first thing I want to do here is we're going to derive the equations. Okay. So I typically don't do this in this class, but I think it's kind of important to see it at least once, just so that you can kind of see the origin of a strong. So let's derive. let's derive the differential equation. Okay. Let's derive the differential equation that governs the displacement within the rod. Okay. Okay. So to do this, what I'm going to do is let's take a small slice from the rod. Okay. I'm going to draw kind of a dotted box right here. Okay. So this box kind of represents a small slice, and let's kind of blow that up right here. Okay. Okay, so this is kind of a small internal slice within the rod itself. Okay. All right. So the thing with elasticity and the thing with elastic equations in general, right? Every single slice or every single part of the rod itself must be in static equilibrium. Okay. And so let's use that to our advantage here. Right? And so in static equilibrium, static equilibrium essentially means that if you sum up all the forces on this slice, the sum of the forces must be equal to 0. Okay. So what are the forces? What are the forces on our slice here? Right? Remember, we took this slice on the internal part of the rod itself. Okay. And so when you take a slice of a structure that's under stress, right? We've seen this in ANSYS, right? So whenever you apply external forces to a structure, you're going to have some internal stresses that develop, right? So think back to our first ANSYS activity, right? When we applied a force onto that plate, we were able to see kind of a stress distribution within the plate. Same thing with ANSYS activity 2. We applied forces to that bike crank, and we saw the stresses develop on the interior. Okay. So I'm going to label 2 stresses here. I'm going to label 1 stress going in this direction and 1 stress going in this direction. Okay. So one side, I'll call that stress N of X, or I'll call the force NX. Now on the other side, we're going to draw a force N of X plus dx, okay? Where the width of the slice is dx, right? So NX, N plus dx. Okay. These are internal forces that develop within the member. Okay. That are mostly developed to keep the structure in static equilibrium. Okay. All right, so we have an internal force on the left, internal force on the right. They may be different. That's why we have that's why we have the N of X plus dx. And then what we also have here is the body force. Okay, and the body force here is B of X plus dx over 2. Okay. And if you're curious about the units for this body force, the units for this body force is a force per length. Okay. Right. That's usually how body forces are defined. So it's usually some force divided by either a length or an area, or most commonly like a volume. Okay. Okay. All right. So now we have 3 forces here. So let's do our sum of the forces. So let's sum up all the forces in this diagram here. Okay, so first we have nx. Nx is a force that's going in the negative direction, so we have minus n of x plus. We have n of x plus dx, and so that is going in the positive direction, so that's n of x plus dx. Okay. And then we have our body force, and so our body force term is b of x plus dx over 2. And to make sure that this gets transformed into units of force, we're going to multiply this thing by dx. Okay. Okay, so we multiply by length. We multiply by the length to get this into the units of force. Okay. So from here, we're going to work on this equation algebraically a little bit. So let's divide the entire equation by dx. And what I'm going to do is I'm going to rearrange the terms a little bit. So we're going to have n of x plus dx minus n of x divided by dx plus b of x plus dx divided by 2 is equal to 0. Okay. So our first term there, our fractional term, this looks very similar to a derivative. And in fact, we can actually turn it to a derivative by taking the limit. Okay. So we're going to take the limit of this expression as dx approaches 0. So we're going to make our slice and turn it much, much smaller. So that's kind of infinitesimally thick. Okay. So what that does is that it's going to take our first term there and turn it into a derivative. Okay. So this is kind of the instantaneous or the derivative right at that slice. So it's dn dx, okay, plus. Then we have our function b of x plus dx over 2, right? So as we take the limit as dx approaches 0, this just becomes b of x, okay? And this is equal to 0 here. All right. And so through that exercise, you can see here that, we basically just, took our structure, we applied a very simple kind of force balance. We took a limit, and what we have here, before we even knew it, is a differential equation. So this differential equation here represents, or it governs, the elasticity of our rod. Okay. So what we can say here is that the time, or the derivative of the normal force or the internal force with respect to x plus the body force b of x is equal to 0. Okay. All right. Any questions on this and how we got to this point here? Okay. All right, so we have a differential equation. It's not the most useful differential equation, because if you remember kind of when we started this, what we're looking for is we want an equation to represent the displacement u of x, okay? So let's work on this equation a little bit, because we were able to derive this equation from first principles. So let's see if we can kind of massage this equation and kind of substitute some terms in order to obtain our displacement here. Okay? In particular, let's look at our normal force, or internal force n. this is a force that kind of develops kind of on the internal, on the inside of our structure, right? So let's plug in for this. And so our internal force is the same thing as multiplying our cross-sectional area, or the area of our structure, okay, cross-sectional area, multiplied by a internal stress. Okay. Okay. Actually, let me label this area right here as a cross-section. Okay. Right, so we have a force is equal to an area times a stress, right? The units work out. Okay. In particular, let's take our stress and let's plug in our typical Hooke's law or linear elasticity. Okay. For stress, sigma of x is equal to E, which is the Young's modulus, times epsilon of x. Okay. So we have stress is equal to Young's modulus times strain. So that's our typical kind of equation there. Okay. And then from here, we're going to plug in for the strain, right? Because we know that strain epsilon is equal to the derivative of the displacement, right? So we have du d, right? That's just the definition of strain. All right. So if we plug all those in, then what we get is the internal force N of x is equal to area multiplied by E multiplied by du dx. Okay. All right, so now that we have an expression for the internal force, let's plug this back into our differential equation. Okay. And so we plug that in, we get d dx of area. Remember, area can be a function of x, and so the area can change. And so let's say that you have a tapered rod or a rod that kind of changes cross-sectional area. We can account for that in this equation. Multiplied by E, okay? It's not really common for the Young's modulus to change because usually you have a structure that's made of one material. But technically speaking, if you have some kind of weird composite material, then you can account for that here as well. Okay. Then we have our strain. So our strain is du dx. We are able to get u into our equations. We're able to get our displacement here. So that's really good. Then we add our body force term, b of x, and then all that's equal to 0. Okay. And this right here is our 1D elasticity equation. All right. So what we have here, just to kind of dissect this a little bit, we essentially have a second order differential equation that we can use to solve for the displacement. Okay. How is it second order, you ask? And so if you look at this first term, you can see here that we have an x derivative on the exterior, and then when we apply that to the interior, this becomes like a second order equation here, right? Of course, if we have terms where the area changes as a function of x, then that's going to make our equation more complex. But the total amount of derivatives, or the total derivatives for our solution, is 2. Okay, so that makes it our second order equation. Okay. So we can now take this equation and solve for its solutions. But in order to do that, we also have to apply boundary conditions. So again, boundary conditions is not something that's strange to us, right? We've done it many times before. It's just that now that we're working with differential equations instead of linear systems, they're going to take a different kind of mathematical form. Okay. We still have two different types, and so we still have our load type boundary conditions or our Neumann type boundary conditions and our Dirichlet or constraint type boundary conditions. Okay. So let's go over both. And so let's go over Dirichlet boundary conditions first. So remember, these are our constraints. Okay. So we apply our Dirichlet boundary conditions in locations when our solution variable is being directly specified. Okay. Okay. So what does that mean? So we want to look for locations where the displacement has a fixed value. And we can kind of tell that without solving the equation. Okay. Okay. So let's look back at our problem geometry and see kind of where those locations are. So if you go back to our problem geometry here, okay, we can see that our bar here, or our truss, or our structure, or whatever, is fixed to the wall on the right side. Okay. And what does fixed boundary condition means? Fixed boundary conditions means that the displacement is going to be 0. In particular, because we have our coordinate system here, what we can say is that the displacement at x is equal to L is going to be equal to 0. Okay. We can say u at x is equal to L is equal to 0. Okay. So that's our Dirichlet boundary condition on one side of our equation. Okay. Okay, so let's go back down here. And so our Dirichlet boundary condition is u at x is equal to L is equal to 0. Okay. We're directly specifying the value of the solution at that location, and we're directly specifying to have a value of 0. Okay. Okay. So Dirichlet boundary conditions pretty straightforward, and actually, they're more straightforward to apply in this form than it was in direct students. Okay. All right, so let's look at our Neumann boundary conditions. So these are traditionally our modes. Okay, so our Neumann boundary conditions, the way we kind of defined these before was that these are conditions that don't directly specify a solution value, but they do affect the solution. Okay. And what you'll see is that now that we're looking at the differential equation side of it, the Neumann boundary conditions are going to take kind of a more specific definition. Okay? Because this definition is okay, but it's kind of vague in its definition. So you'll kind of see what I mean here. Okay. So our Neumann boundary condition in this particular case is an applied compressive stress on the left side of the wall. Okay. In other words, we have an applied compressive stress at x is equal to 0. Okay. And so if we draw that out, okay, and in fact, let me draw it like this. And so let me go ahead and let's draw a free body diagram here. Okay. Okay. So T there is our applied compressive stress, right? There must be equilibrium, right? So there must be equilibrium everywhere. And so to oppose this, we have N of 0, where N of 0 is the internal stress at x is equal to 0, or internal force at x is equal to 0. Okay. All right. So let's make our force balance, right? So under our force balance, okay, we have T, okay? T here is a stress, and so to get a stress into a force, we have to multiply by area, okay? So T multiplied by the cross-sectional area at x is equal to 0. This must be equal to, of course, you know, there's a sign change here, but you know, we'll assume that that's all good. Okay. Actually, no, let's do this properly. Okay. We have T bar times A0 plus N of 0. This must equal to 0. Okay. Let's plug in for N of 0. Okay. And so if we use our expression before, the normal force is equal to the cross-sectional area, A, multiplied by the Young's modulus, E, multiplied by the strain, du dx at x is equal to 0. Okay. And so we plug that expression in, we get T bar times A of naught plus A of naught, E of naught, du dx at x is equal to naught, to 0. All that's equal to 0 there. Okay. Okay. We have A of 0 in both terms, and we have this equation equal to 0, so we can divide the entire equation by A of 0, cancel that out. Okay. And so if we kind of work on this algebraically a little bit, we move the T bar to the other side. What we get is quantity E times du dx. Okay. Both of these are evaluated at x is equal to 0. These are going to be equal to minus T bar. Okay. So this right here is our Neumann boundary condition. Okay. Any questions on how we obtain that result there? Okay. All right. One thing I want to highlight here, and it kind of expands our definition of Neumann boundary condition a little bit, is that this boundary condition here involves the derivative of our solution. Okay. Okay. And so when you mention, or whenever you mention a Neumann boundary condition or a load type boundary condition, mathematically what's happening is that it's a relationship between the derivative of the solution and some kind of applied force, okay? And so that's kind of the more precise definition of Neumann boundary conditions. That a Neumann boundary condition involves the derivative of the solution in one way. Okay. So now that we've stated the mathematical form of the boundary conditions, along with the governing differential equations, we are ready to kind of state the full strong form of our equations. Okay, so the strong form kind of is comprised of three different equations, kind of all coupled together. Okay. All right, and so on the one hand, we have our governing differential equation. So the differential equation governs the behavior of our structure kind of all throughout its member. Okay, so that was d dx of e times a du dx plus b of x is equal to 0. Okay, so we call this our governing equation. And usually what we present along with this is the domain of applicability. And so what we say that this is valid on the domain of 0, which is less than x, which is less than L. Okay, so this right here is our domain. Right. And then we also have our boundary conditions. And so our boundary conditions is, first we have our Dirichlet boundary condition, u and x is equal to L, equal to 0. Okay. And then we have e times du dx at x is equal to 0 is equal to minus t bar. Okay? And these two things combined are our boundary conditions. Okay. All right, so those, I guess it's technically 4 expressions, but a governing equation, our domain, our boundary conditions, that right there is the strong form of our equation. Okay. So now let's go about solving this, right? So the way you solve these differential equations, it's we're not going to do a comprehensive review on differential equations here. This is mostly just to kind of jog your memory on these things. Okay. All right, so let's do a very simple example. So let's consider the following structure. So let's say that we have a structure that looks like this. So let's say we have a bar here. We'll say it's fixed on one side. Sounds like a party. All right, and on the other side, we're going to be applying a pressure force. Okay. So this geometry is a little bit different than what we had previously. Okay. So previously we had the fixed constraint on the right side. This time we have the fixed constraint on the left side. Last time we had the pressure boundary condition on the left. This time we have it on the right. Okay, but we can still apply the same methodology here. So let's say that the total length of this structure is 1 meter. Okay. We need values for the Young's modulus. So the Young's modulus, very softly here, is 100 kilopascal. And the cross-sectional area is 0.1 meters squared. All right, so with this information, let's solve for the distribution of displacement within the structure. Okay, so essentially solving for u of x. Okay. So we're going to be solving the strong form of this equation because that's all that we've learned so far. So let's start out by writing out our differential equation. All right, so our differential equation, we have d dx at e times a du dx plus b of x. Okay. This is all equal to 0. Okay. All right, so this is our most general form of this differential equation, but a lot of times you can simplify it based on your specific problem. Okay. So in this case, we don't have any body force, so the problem didn't mention anything about electromagnetic force. Our rod here is horizontal, so there's no gravity force, at least not in the x direction. Okay. So we can say this is equal to 0. No body force. The other thing that we can say is that the Young's modulus and the cross-sectional area are constant in this case, right? And so you look back at the problem here, E and A have a fixed value, right? If those were functions of x, or if those were going to vary, then we'd have to take their derivatives. But since these are constant, we can pull these out of the derivative. Okay. And so if we do that, then our differential equation here is E times A. Okay. We have d dx of du dx, and so that's going to be a second derivative. So this d squared u dx squared. Okay. And that's going to be equal to 0. We can simplify this a little bit more. We know that since E and A are non-zero, we can divide both sides by that. Okay. You divide by EA, divide by EA. Okay. This, of course, is just going to simply cancel out EA. And so our differential equation in this case actually ends up simplifying quite a bit. Is that we have d squared u dx squared is equal to 0. Okay. All right. And so with such a simple differential equation like this, we don't have to employ any kind of advanced methods. We don't have to do any characteristic equation or anything like that. We can just simply integrate to solve. Okay. So let's apply integral on the left-hand side and integral on the right-hand side, okay, with respect to x. So our integral here is going to be with respect to dx. So on the left-hand side, the integral is going to cancel out with one of the factors of the derivative. And so we're going to have du dx on the left-hand side, okay? On the right-hand side, we have integral of 0. Integral of 0 is just 0. But, since we are doing an indefinite integral in this case, right? Our integrals don't have any bounds. We need to add an arbitrary constant. And so this can be du dx is equal to, we'll call that constant c1. So this right here is an arbitrary constant due to that's an arbitrary constant due to the indefinite. All right, so we're going to do that again because we don't quite have u of x yet. So we're going to apply another integral here with respect to x. Okay. And so on the left-hand side of this expression, we're going to have u of x. Okay. And then on the right-hand side here, we have c1. Integral of a constant is just x. So we have c1x. And then just like we did in the first step, we're going to add an arbitrary constant, c2. I'm starting to get competitive, I feel like I'm competing against what's happening out there. All right, so that's our general solution. Okay, so for cases where you don't have a body force and you don't have a a varying cross-sectional area or varying properties, your solution is very simple. You can just simply integrate and get your solution like this. Any questions on this so far? Okay. All right, but we're not quite done yet. And so in order to get our full solution here, we have to apply our boundary conditions. And the reason we're applying the boundary conditions is we need to solve for values for C1 and C2. Okay. So let's go ahead and do that. So we have our two boundary conditions here. And so our two boundary conditions, the first one that we have here is that u of x or u of 0, right? This is our Dirichlet boundary condition. And so since we had a pin support on the left-hand side of our bar, that means u of 0 here has to equal 0. Okay? So let's go ahead and apply this boundary condition. So let's take our general solution, u of x, and let's plug in x is equal to 0. So everywhere we see x, we're just going to plug in 0. Okay. So we have C1 times 0 plus C2. And then according to our boundary condition, this is equal to 0. Okay. All right, so the C1 0 is going to cancel out. And then what we get from here is that C2 is equal to 0. Okay. All right. Then we have our other boundary condition. So our other boundary condition is our Neumann boundary condition. Okay. This boundary condition is applied on the right-hand side. Okay. And so we're going to flip the sign of our typical boundary condition. So our typical boundary condition is E du dx. Okay. So our Neumann boundary condition here is applied at x is equal to L. So we're going to plug in x is equal to L there. Okay. And this is going to be equal to, normally it's minus t bar, right? So that was our kind of our boundary condition before, but since our force here is tensile, okay, we're going to flip the sign here. So we're going to say this is going to be equal to a positive t bar. Okay? And so our t bar in this case is 100 Pascal. Okay. All right, so let's go ahead and plug in. So du dx, to get du dx, we have to kind of go back into our solution here. So we know that du dx and this problem is equal to just C1, right? So that's what we obtained just kind of midway through our solution. Okay. Okay. And so we multiply that by E. So E here is 100 kilopascal. Okay. We multiply that by our solution derivative, which is just C1. And this is all equal to 100 Pascal. Okay. Okay, and then from here we just solve for C1. So the units are just going to cancel out. Here we're going to solve this. We're going to convert it to Pascal. So 100 times 10 to the third Pascal multiplied by C1 is equal to 100 Pascal. Okay. And so we solve for C1. C1 in this case is 0.001. All right, so let's go ahead and plug both of those in. And so we plug both those in, we get u of x is equal to 0.001 x. Okay, and so that's our strong form solution. So our strong form solution is you take your differential equation, you solve for its general solution, and then you incorporate the boundary conditions. All right, any questions on how we got to this point here? Okay. All right, so we have about 15 more minutes today. And so what I want to do with this last time is to just introduce the weak form to you, and then we'll go through the main derivation next time. Okay. So first thing I want to say is that, even though we call it the weak form, there's nothing inferior about it. So I think, just by the terminology of strong versus weak, you would think that strong form is superior or has better qualities. It's nothing like that. So the weak form is, it gets you, if you solve it exactly, it gets you the same solution as before. So whoever I understand why they named it like this, but at the same time, it's terrible for your first understanding, because there's a lot of connotation, there's a lot of kind of assumptions that come with the word peak. Okay? So there's nothing really weak about it. The term comes in that, or the reason it has that term is that you can enforce certain conditions in a more weak form. And that means basically kind of in a more approximate form. And it's also given that name because it's a lot easier to find approximate solutions to a weak form than it is a strong, right? But it has nothing to do with kind of accuracy or usefulness. It's just the name. Right? So weak form is nothing wrong. Okay. And so with that, I wanted to highlight, even though the strong form, I think, is what people typically learn when they first learn about differential equations, there are some drawbacks, or I would say some inconveniences with the strong. These don't really seem like that big a deal for for 1D problems. We just kind of did an example just now. But just know that a lot of these problems kind of get exacerbated when you get into higher dimensions and higher order equations as well. Okay. So there are two main issues, I'd say. Not really issues, but they're kind of inconveniences. Okay? Okay. The first issue is the order of the derivatives. Okay. And so if you look at our strong form equations, right, even for the very simple one that we just did, it is a second order equation. Right? So that means the highest order derivative is 2. And that's actually very, very common in engineering. So a lot of physical phenomena have these kind of second order equations, right? And then once you get to electromagnetism, it gets to fourth order, right? So generally speaking, the higher your order, the higher order of your derivative, the more complex your solution is going to be. Okay? So it would be great if there's a way that we can solve a similar problem that gets us the same solution, but with a lower order derivative. So that's the main thing, right? Or that's one of the main things is can we weaken the order of the derivative and still get the same solution? Number two. So the other thing that's a little bit kind of inconvenient about the strong form is how we apply the boundary conditions. And so if you look at how we applied the boundary conditions in our last example, we kind of had to do it as a separate step, right? So the first thing that we did was we solved our general equations, and then we applied our boundary conditions onto that to get our solution. Okay? The boundary conditions. Okay? So the boundary conditions are applied separately from the main equation. It would be really nice if we had kind of one kind of unified form that not only incorporated the governing equations, but also the boundary conditions as well. Okay? So these are the two main things that the weak form attempts to address, and it actually makes things a lot easier for us to form finite element solutions as well. Okay. Okay. So how do we get the weak form, right? So how do we take our strong form solutions? How do we try to solve these two issues and get something that we can actually solve? Okay. Okay. So to obtain the weak form is kind of a two-step process. Okay. And they involve two steps that you probably would never have thought of before. Okay. And so the first step is to multiply your entire governing equation by something called a weighting function. Can't tell if they're like doing karaoke out there or something, or if it's just like. Okay. And so we'll call our weighting function w of x. Okay. So let me kind of show you what that looks like. And so for our differential equation here, so we have our differential equation d dx of e times a du dx plus b of x equal to 0. Okay. What we're going to do is we're going to multiply this entire equation by w of x. Okay. And so that gives us w of x d dx of e times a dx plus, we're going to distribute that w of x to the b of x to the body force term as well. So we have w of x, b of x. Okay. All that's equal to 0. Okay. So we're going to multiply by this weighting function, right? You probably have a lot of questions about the weighting function, right? But we'll kind of save that for next time. The second thing that we're going to do is we're going to integrate this entire equation over the problem domain. Okay. All right, and so if we do that, so we have two terms here, and so our two terms, we can integrate them separately, right? And so we're going to have our first integral from 0 to L of w of x d dx of e times a du dx dx, okay, plus integral from 0 to L of wx, v of x, dx. Okay. All that's equal to 0. Okay. And the next step, which we're going to save till next time, is the kind of the methodology that we're going to use to reduce the order of the derivative, right? Because if you look at this first term here, this chunk that I've highlighted in red essentially is a second order derivative. Okay. Because if you think about our example where our E and A are constant, then that d dx gets applied to du dx, right? So what we can do now that we have our equation this form is we can apply something that you probably thought you would never see again after Calc 1 or Calc 2, is we're going to apply integration by parts. Okay. Because what integration by parts is going to allow us to do, it's going to allow us to essentially move some of the derivatives around. So we're going to move one of the derivatives from u, and we're going to put that derivative onto w, our new friend, the weighting function. Okay. This seems like kind of voodoo magic here, but trust me, it's going to make sense. It's just that today's not the day for it because we're almost out of time. All right, any questions on this before we wrap it up for today? Okay, so I wanted to end a little bit early just because I have your exam here, so you guys can come up and pick it up. Please look over your exams because I was trying really hard to kind of finish them by today. So if I made any mistakes, or if you want me to take a look at a question again, you think you deserve more points, I'm always happy to take a look. So please read the exams, read the comments that I posted, and then if I made any mistakes or if you want me to look at it again, just let me know. Okay. All right, so thank you guys for coming today. If you're on Zoom, I'm going to bring in the exams again on Thursday, so you can bring it. You can come then, pick it up. But thank you guys for coming today. Thank you guys for I don't know if you guys are hearing over Zoom, but there's very loud music going on outside. So thank you guys for being patient today, and I will see you all on Thursday. Oh yeah, I will. They're at my house, though. So probably tomorrow when I'm working. Oh, sweet.